All right, let's do example number 2. We may do example number 1 in class. If we don't, you can do it on your own. It's just finding RPM. But example number 2 here, with these motors, I've said, same with the linear motors, we need to find what it is that we have that we're working with. We're working with these terms right here. Here's my RPM, revolutions per minute. Right here is my efficiency, eta, at rate of conditions, and assume no rotational losses. That's like saying no mechanical loss, no friction loss. And the main thing equation-wise is that that means that the P mechanical loss equals 0. All right, so that P mechanical loss equals 0 because it's a no rotational losses, right? On this power flow diagram over here where it says mechanical loss, there's no arrow coming out on this particular problem. Then I have my KV, which is a machine constant. Okay, so if it said find a machine constant, that is KV. And then find the back EMF, that is EA. That stands for armature, right? So remember, A stands for armature, right? So if it said find the armature current, right, armature, there we go. Armature stands for armature, or if it said find the armature windings, the current going through the armature windings, or find the E induced in the armature, that would also be the same thing, right? Stands for armature. If I think about my motor, that's what has the current flowing through. So this part right here, it's spinning inside the magnet. Lots and lots of wires together make the windings. Okay, so let's solve now what we know, what we need to find. We need to find KV. First step for me is I'm going to use the Pn equals V dc IA. I know both of those, and I have an efficiency, and I'm going to use that to get to what I need to know. So I have VDC equals IA, 120 volts. I is 15 amps. And that together makes 1800 watts, which would be equal to 1.8 kilowatts. And I take my efficiency. That equals 0.85. That equals P out divided by P in. And I'm going to get to P out equals efficiency times P in. So 0.85 times 1.8 kilowatts. And my P out comes to 1.53 kilowatts. If I think about these equations of the power developed, that's where the machine constant is. I know I'm going to use something in the middle of that power flow diagram. That's the only place where KV is. So for mine, I'm looking at the power developed equals, this is at the bottom of the power flow diagram. Can I highlight? Right here. Okay, I'm looking at this part right there. So that power developed equals P mechanical loss plus P out. And since my P mechanical loss was 0, my power developed equals my power out. So this right here, 1.53, is also my power developed. So I look at what else do I know? I know that the power developed equals KV IA omega. Do I know omega? Not quite. I do have the RPM, so I can get it. Omega equals 2 pi. Put that 3600. This is from the top right equation up here. Okay. 3600 divided by 60, and it's going to convert my RPM into radians, which is 2 pi 3600 divided by 60. We'll go with 120 pi. Okay, so now I rearrange. KV equals P developed divided by IA omega. That power developed, 1.53 kilowatts divided by 15 amps, 120 pi. And I'm left with 270.56 millivolt seconds. If you needed to write the radians per second to see that, you could, but that seconds is going to go up top, and the watts divided by amps gives me volts. So there's part A. Part B, I'm asked to find the back EMF. Well, if I have EA, I'm trying to find it with, you could do the power developed equals, actually we'll do it both ways. So first equation I see right here, EA is equal KV to 70.56 times the 120 pi, and my EA is 102 volts. The other way would be to say that my power developed equals EA IA, the armature, and the EA equals the power developed divided by the IA, and that is 1.53 kilowatts divided by I of 15 amps, and my EA also comes out to 102 volts. So it checks out.